All right, so let's do a little spectroscopy problem here. So what we have is a hydrogen atom that emits a photon as it relaxes from the third excited state to the ground state. And we want to figure out what the wavelength in nanometers of the photon that is emitted. Okay? And so there are quite a few things going on in this problem, and I think we should start by drawing an energy state diagram showing this transition so we can basically draw what we're doing. Okay? So let's go ahead and draw one. All right, so there's the energy axis, okay? And n equals 1 is the ground state. Put on n equals 2, n equals 3. Okay, these should get closer together as we go up. And how far up do we need to go? Okay, so let's look at third excited state. Okay, so what is that? So the third excited state, so the ground state is n equals 1. First excited state is n equals 2. Okay, second excited state, n equals 3. So we need to go up to n equals 4. Okay, for the third excited state. All right, and so what is happening here is that this hydrogen atom is excited, and it's in the third excited state, and it's going to relax down to the ground state, and in the process release some energy that's going to be in the form of a photon. So it's going to release a photon of a certain wavelength, which is a little packet of energy. Okay, and this energy is going to be negative because it's releasing energy. Okay, so let's go ahead and also write down the Bohr equation. Okay, which for hydrogen is very similar in form to the Rydberg equation. Okay, so negative 2.18 times 10 to the negative 18 joules. Oops, actually here, let me move this thing over. It's not enough room. Okay, so go back and let's try to squeeze it in right here. So delta E atom, so this is the change in energy of the atom. In this case, it's our hydrogen atom. And it's going to be negative 2.18 times 10 to the negative 18 joules times z squared. And then it's going to be 1 over n final squared minus 1 over n initial squared. Okay? All right, so here, let's just fix that little one too. Okay. All right, so what we have here is the Bohr equation, and we just need to figure out how to fill things in so that we can calculate this change in energy of the atom. Okay? Now these n's here, they relate to the quantum number n, so principal quantum number n, all right? And we are going from the third excited state, so that's n initial, okay? So that's going to be equal to 4, and then n final, because we're going to the ground state, that's going to be 1, okay? And then now, Z, that's the atomic number for whatever atom or ion we are looking at, and it's hydrogen, so Z is going to be equal to 1, okay? All right, so let's go ahead and plug things in and calculate this change in energy of the atom. Okay, so I'm going to change this color here. All right, and let's fill in the information, okay? So I'm going to actually write it right down here. So delta E atom okay, negative 2.18 times 10 to the negative 18 joules times 1 squared, okay, which of course is just going to be 1, and 1 over 1 squared, because that's n final, minus 1 over n initial squared, which is 4, and that's going to be squared. Okay? All right, so let's go ahead and just do the calculation. All right, so we're going to have negative 2.18 times 10 to the negative 18 joules times 1, and it's going to be 1 minus 1 divided by 16, okay? And that's going to give us 0.0625, all right? And when we put that in our calculator, we are going to end up with negative 2.04 times 10 to the negative 18 joules. Okay? All right, so that's the amount of energy released by the hydrogen atom as it relaxes from the third excited state to the ground state. Okay? That's the amount of energy released. Now that amount of energy is exactly equal to the energy of this photon that is released, and the only thing we need to do is remember that energies of photons are always positive, so we have to remove this negative sign because the atom released energy, but it released it as a photon, and that's a positive quantity. Okay? And so let's calculate, now we know the energy of our photon, okay? So the absolute value of delta E atom is equal to the energy of our photon, okay? So E photon is equal to 2.04 times 10 to the negative 18 joules. All right, so now we're ready to be able to calculate the wavelength, okay? So E photon is equal to hc over lambda, okay? And we're just going to rearrange this and solve for lambda. And that's going to be hc over E photon, okay? Fill things in, 6.626 times 10 to the negative 34 joules times seconds, multiplied by 2.998 times 10 to the 8th meters per second, speed of light, okay? And energy of our photon is 2.04 times 10 to the negative 18 joules, okay? And let's go ahead and cross out, cancel out units, and we end up in meters, which is good because we are looking for a length, okay? So having meters is good, and when we run those numbers, we are going to end up with 9.74 times 10 to the negative 8 meters. Now I'm going to write this on the next slide, so I'm going to go to the next slide right now. Okay, and so here's our wavelength in meters, okay? So when we do the calculation on the previous slide, then we're going to end up with this. Okay, now let's go ahead and convert this guy to nanometers because the problem asks for the wavelength of the photon that is released in nanometers. Okay, so 9.74 times 10 to the negative 8 meters, okay? And let's go ahead and do our conversion. So we have 1 meter is equal to 10 to the 9th nanometers, okay? And so when we multiply that out, we're going to get 97.4 nanometers. Okay, so that's a pretty short wavelength. So big energy transition, short wavelength photon, quite a bit of energy.